forgot to say earlier, you're going to be watching a video to begin with based on what we're going to do today, which is going to be going over linear, quadratic, and exponential models. The first thing you need to do before I start the video, however, is to copy these tables down. And instead of copying them like he has them, copy them one after the other. So you're going to be needing to write the size. So copy them one after the, doesn't matter which way you do it. Put this one at the top, that one in the middle, and that one on the bottom. But make sure you get those tables first before I start the video. Move where? As long as you're not talking. The video is off of Khan Academy, and he does a good job of explaining this first part. So I'm going to let him do this, and then I'll stop it periodically to let you get caught up just in case you need to.
Deidre is working with a function that contains the following points. These are the x values, these are y values. And they ask us, is this function linear? In this video, we're going to play a bit of a game. I have 3 different data here, and we need to figure out which of these data sets come from either a linear, quadratic, or exponential function. And just as a reminder, a linear function is of the form y is equal to mx plus b. A quadratic is of the form y is equal to ax squared plus bx plus c. And an exponential is of the form y is equal to some constant, let's call it a, times some number to the x power. Now, the way to tell them apart, and I'm going to actually show you, it'll probably be intuitive for you for a linear function, and maybe even for an exponential. The quadratic, the technique I'm going to use might not be intuitive, and I'll actually prove it to you in the next video, or at least show you an example in the general case of why it makes sense. But the way to tell a linear function is that when you increment x by a constant amount, y will always change by a constant amount. So when you always increase x by 1, y should always increase by a certain amount. So let's just using that as our kind of our first guideline. Let's see which of these represents a linear function. So over here, so in all of these examples, as we go from one data point to the next.
So as you're going through on your ESC, you're going to have 3 different types of equations that you're going to be responsible for, just like you said. The linear, which you know is the y equals mx plus b. The quadratic, and its standard form, ax squared plus bx plus c. And then the exponential, which was the last one we covered. And we looked at it as a times b to the x power. Those are the 3 that we looked at. He used R instead of B, but I just wanted you to make sure you've got that B on there because that's what's going to be on your calculator. They're going to give you on the ESC, probably on the first part of the ESC, the non-calculator part, they're going to use tables, which is what he's going over here. And you're going to have to figure out which one is it. And their choices will be linear, quadratic, exponential, or it may say neither. So it's going to be one of those 4. So you need to pay attention to what's going on here. It's very easy questions to do and really easy to answer as long as you know what's going on.
We're increasing x by 1. It's very important that you pay attention to that because if you weren't, you'd have to adjust to things a little bit. But in all of these, we're always increasing x by 1. So let's look at our change in y's. When we go from the first data point to the second data point, our change in y is 60. When we go to the second to the third, our change in y is 90. So that immediately tells us we're not dealing with a linear function. When our change in x is 1, our change in y here is 60, then it's 90, and then if you go here, what is it? It's like 135. So this one is clearly not linear. Let's look at this one over here. Our first change in y is 2. Then our next change in y is 0. Once again, not linear. As we increment x by a constant amount, our y does not increase or decrease at a constant amount. So once again, this one is not linear. Now let's look over here. Once again, we're...
You understand what he's saying? When you subtract 180 from 120, you get 60. When you subtract 270 from 180, you get 90. So in order for this to be a linear equation that he has, these numbers have to be the same. And they have to be the same all the way down. It's called the first difference, meaning you're subtracting and the first time you're doing it. So the first difference has to be a constant. Doesn't matter what that constant is, as long as all of these are the same. So instead of going down through here and doing them all, he's realized once he started right here and he had 60 and 90, that's not a linear one. And once he started 6 minus 4 to 2 and 6 minus 6 to 0, he realized these numbers aren't the same, so we know it's not linear. I just want you to understand the vocabulary he's using.
Increasing x by 1 on every data point. And when we go from this first data point to the second data point, y decreases by 3. And we go from the second to the third, once again, y decreases by 3. Third to the fourth, y decreases by 3. 1 to negative 2, once again, decreases by 3. And we just keep decreasing by 3. So whenever we change x by 1, when we increase x by 1, y goes down by negative 3. So we actually have a constant slope. We could say our change in y over change in x is equal to, when x goes up by 1, y goes down by 3. This is the definition of slope. This is the m in this equation right here. Our changes are constant. So this one right here is linear. This one right here is linear. Now quadratic, there's an interesting, we could call it a trick right now because I haven't really showed you why it works. But in a quadratic, your changes in y, the changes in y are not going to be constant, as was the case with the linear, but the change in the changes of y will be constant. Let me write that down. It probably makes no sense to you right now, but when you see an example, it'll be kind of fun. Change in y constant.
That really just means the second
Constant.
difference.
Let me show you what I mean. So over here, let's look at this first one over here. So we went from 120 to 180, that was an increase of 60. 180 to 270, that was an increase of 90. And we went from 270 to 405, which is an increase of 135. Now when I talk about the change in the change of y, these are the change in y's. What are the change in the change of y? Well, we had a change of 60, then we had a change of 90. So that was a change in the change of y of 30, or a difference of the difference. You could view it that way if you like. And we go from, then we had a change of 90, and then we had a change of 135. So the change in the change, let's see, that is 45. So here the change in the change in y, or the difference of the difference, is not constant. We grew by 60, and then we grew by 90, which is 30 more than 60. Then we grew by 135, which is 45 more than 90. So this is not constant over here. So this tells us that this is not a quadratic function. Now let's look at this over here. The change in y, let's write that down. This clearly was not linear. We increased by 2 here, increased by 0 here, increased by negative 2 here, increased by negative 4 here, increased by negative 6 there. The change in y's are definitely not constant, but let's look at the change in the change of y's. So we increased by 2, then we increased by 0. So this was a negative 2 in the change of y, or the difference of the difference. Then when you go from 0 to negative 2, we changed by 0, then we changed by negative 2. That is a change in the change of negative 2. Then you go from negative 2 to negative 4, a change in the change of negative 2. This one's starting to look quadratic. We changed by negative 4, then we changed by negative 6. Once again, a change in the change of negative 2. So this data right here fits our requirement for a quadratic. And I'm just kind of giving it to you as a trick right now. In the next video, I'll actually show you why this works. I'll show you an example, or just so you get the gut feeling of why it should work. So this one right here is quadratic. So you might say, hey, Sal's give us 3 examples. One of them is going to be linear, one of them is going to be quadratic, one is going to be exponential. This one's probably going to be exponential, and you are probably right. But let me give you the way that we can figure out if something is exponential. So when x increases by 1 in an exponential, you should always have a constant multiplying factor. So when you go from one term to the next term, they should be a similar ratio from one to the next. So instead of just subtracting, in this case, 120 from 180 and 180 from 270, to test for an exponential function, what you want to do is check whether the ratio of, when you increment x by a constant amount, whether the ratio of the y's are the same. So when we increased x by 1, y went from 120 to 180. So it increased by 18 over 12 is 1.5. So we went from this term to this term. Let me clear all of this stuff out here. Let me clear this. So when we went from here to here, this was times 1.5. And then when we go from 180 to 270, once again, that looks like we're going times 1.5, right? Half of 180 is 90. Add that to 270. So once again, we're increasing by 1.5. 270 to 405, half of 270 is 135. That's how much we're increasing by. So once again, we're increasing by 1.5. So every step of this way, we are multiplying the previous term by 1.5 to get the next. And that actually tells us that this right here is a 1.5. But our point here isn't to actually figure out the formulas. The point here is to classify them. So now we know definitively that this right here, at least given the data we have, is an exponential function. Anyway, hopefully you found that fun. Deidre is working with a function that contains the following points. These are the x values, these are y values. And they ask us, is this function linear or non-linear? So linear functions, the way to tell them is for any given change in x, is the change in y always going to be the same value? For example, if for any one-step change in x, is the change in y always going to be 3? Is it always going to be 5? If it's always going to be the same value, you're dealing with a linear function. If for each change in x, so over here, x is always changing by 1. So since x is always changing by 1, the change in y's have to always be the same. If they're not, then we're dealing with a non-linear function. We can actually show that plotting out. If the changes in x were going by different values, if this went from 1 to 2 and then 2 to 4, what you'd want to do then is divide the change in y by the change in x, and that should always be a constant. In fact, let me write that down. Linear, if something is linear, then the change in y over the change in x, always constant. Always constant.
What he's saying here, just like what he did before. Before he said 14 minus 11 was 3. 19 minus 14 is what? 5. So 14 minus 11 is 3. 19 minus 14 is 5, or 3 and 5 is the same thing. Now, this is not going to be linear, but what over here, they're each increasing by 1, right? So 5 minus 4, 4 minus 3. So this is important in that these need to be the same numbers. Like you don't want to skip from 1 to 3 and then go to 4 and 5. So, and they may try to trick you that way. So always check to make sure these are going up by the same amount. But when he's talking about changing y over changing x, you've seen that. Where have you seen y over x? What does that mean? True. But what have we been working with that is y over x? The slope. This is what it means by linear, because we're looking at the slope. That's why it's a linear function. Or a non-linear function, whichever the case is.
Now, in this example, the change in x's are always 1, right? We go from 1 to 2, 2 to 3, 3 to 4, 4 to 5. So in this example, the change in x is always going to be 1. So in order for this function to be linear, our change in y needs to be constant, because we're just going to take that and divide it by 1. So let's see if our change in y is constant. When we go from 11 to 14, we go up by 3. When we go from 14 to 19, we go up by 5. So I already see that it is not constant. We didn't go up by 3. This time we went up by 5. And here, we go up by 7. And here, we're going up by 9. So we're actually going up by increasing amounts. So we're definitely dealing with a non-linear function. And we can see that if we graph it out. So let me draw, I'll do a rough graph here. So let me make that my vertical axis, my y-axis. And we go all the way up to 35. So I'll just do 10, 20, 30. Actually, I could do a little bit more granular than that. I could do 5, 10, 15, 20, 25, 30, and then 35. And then our values go 1 through 5. I'll do it on this axis right here. They're not obviously at the exact same scale, so I'll do 1, 2, 3, 4, and 5. And so let's plot these points. So the first point is 1, 11. When x is 1, y is 11. This is our x-axis. When x is 1, y is 11. That's right about there. When x is 2, y is 14. When x is 2, y is 14. That's right about there. When x is 3, y is 19. When x is 3, y is 19. Right about there. When x is 4, y is 26. When x is 4, y is 26. Right about there. And then finally, when x is 5, y is 35. When x is 5, y is 35. Right up there. So you can immediately see that this is not tracing out a line. If this was a linear function, then all the points would be on a line that looks something like that. That's why it's called a linear function. In this case, it's not. It's non-linear. The rate of increase as x changes is going up. 2 videos ago, I told you that when you're dealing with an exponential function, that when you increase x by a constant amount, that the y values will increase by a constant factor. When we increased x from 0 to 1, we increased y by a factor of 1.5. We multiplied 1.5 times 120 to get 180. When we increased x by 1 again, once again, y increased by a factor of 1.5. We multiplied 1.5 times 180. What I want to do in this video is to kind of quickly show you, just going from the basic definition of an exponential function, why this is the case, why this works for exponential functions. So let's just start with the general exponential. Y is equal to a times r to the x. And let's look at some x values and then the corresponding y values. So these are my x values. Those are my y values over there. Now let's say that x is equal to, let me just pick an arbitrary number. Let's say that x is equal to b. I haven't used that variable yet. And what's y going to be equal to? It's going to be equal to a times r to the b power. Now, let's increase x by 1. This would also work if you increased x by really just a constant factor. But let's increase it by 1. So we're now going to look at x is equal to b plus 1. Then y is going to be equal to a times r to the b plus 1 power. Let's do it one more time. Let's increase x by 1. You get b plus 2. And now now y would be a times r to the b plus 2 power. Now let's see what happens when you take the ratio of each successive y term that corresponds to the x terms when you increase x by a constant factor. Notice every time we increase x by exactly 1. If this is 0, this is 1, this is 2. If this is negative 5, this would be negative 4, this would be negative 3. So let's see what happens with our y. So over here, if we look at the factor that y changed by, we could just divide a r to the b plus 1 by a r to the b, and what do we get? Well, you might already recognize you could use straight up exponent rules right here. The a's cancel out, and then this is going to be equal to r to the b plus 1 minus b. Same base, if you're taking the quotient, you subtract the exponents. So this is just going to be equal to r. That's just going to be equal to r. Let's see what happens when we go from here to here. Once again, take the y value when x is equal to b plus 2. So a r to the b plus 2 divided by the previous y value divided by a r to the b plus 1. These cancel out, and we're left with r to the b plus 2, r to the b plus 2 minus b plus 1, which is equal to r to the b plus 2 minus b minus 1. These cancel out, 2 minus 1. Once again, you're just left with r. So hopefully that satisfies any curiosity you might have had of why you're able to use that as the way to evaluate whether this data was exponential. Why we're able to just say, hey, let's take this term, divide by the previous term, and...
All right, here, before I turn this off, I want to make sure, does everybody have this down? Key points in here, when it's linear, that first difference is constant. Doesn't matter what the number is, as long as it's the same all the way down. For quadratic, it's not the first difference, but the second difference. So the second time you subtract, you get the same number, same constant, whatever it is. And then on the exponential, you're not, you saw where he subtracted before and he got 60 right there, and then he got 90 right there. So if you're looking at it, remember exponentials either go up really fast or they go down really fast. They increase quickly or they decrease quickly. So on these, you're going from 120 to 911, which is a very fast increase. So that's why he's going through and saying 180 divided by 120, or 270 divided by 180, but still you get that same difference on there. As long as everybody's got that, we're going to go back to...
and see what number we get. This term divided by that.
There we go. Okay. So I'm going to add some different things in here on what I put before. So a linear, remember a linear is just, I just drew a quick graph here. It doesn't have to be anything perfect, but a linear is going to be just a straight line, which we work with over and over and over. A quadratic, what does a quadratic look like? What general shape is it? It's a U. Okay, so it's a U. And then exponential starts out really small and then increases really fast, or just the opposite, starts really high and increases. So different kinds of graphs. So you've got to know to go to from the equation to the graph to the table. There's three things you need to know how to go from: the table, the graph, and the equation. So in that, or on that, on that packet that you got there, turn over to the back, right here on the second page. That's it we're going to do on the last two pages. On the next to last page, here's where it talks about the first and second differences. It's in your packet there. So it's the next to last page. Next to last page. Here's where those tables are. That's where it starts talking about first and second differences. So in those tables, you can tell in example 1, he subtracted, we got the -2, and then example, these are not the forms that he has up there. But in example 2, he subtracted, and the first time he subtracted, he didn't get it, or there isn't a constant. The second time he subtracted, he gets a constant of 2. And then the third one, what do you notice about in example 3? The y value and what the first difference is. What do you notice about those? On example 3, look at the y values and look at the first differences where you subtracted. They do start out as fractions, true. What else do you notice? Do what? double, okay? You're what? You're even. True. Anything else? Does nobody pick up on the fact that they're exactly the same? The y values and the differences? The y values in the table and then the differences right below there? So they're following a pattern? And that's another key on the exponential. Sometimes, not all the time, but sometimes they will mirror whatever the y values are. See, that's also a hint there. And then of course they've got the graphs over there. So turn over to the back of that page, and we've got a bunch of tables there that we're going to go through. Now, so on the back of that page, there's all these tables listed out. In fact, I think there's 16 tables here. Everybody see those? 16 tables. Okay. You're going to do, okay, I'm going to pick 4 of these, and you're going to do these right there. You do them in your notes, copy them in your notes, do them on the table, whichever one you want to do. So let's do 1, 2, 4, and 15. So 1, 2, 4, and 15. I'm going to copy them down while you're writing. So you're doing 1, 2, 4, 15. So you're finding the common differences. And you're trying to decide is it linear, quadratic, or exponential. You've got your calculator, so nobody should be sitting there doing anything. Anyway, so let me go back since I forgot to record that part. Maybe. So there's our 4 tables, 1, 2, 4, and 15. Now we're going to go to the equation. I'm going to write these back up here real quick. You should have these in your notes already. I'm just going to put them back up here. So we're going to use the calculator and put these points in our calculator to see which top they are. Right. You may remember when we started doing lines and we were putting them in our calculator, how did we put the points in there? We wanted a graph, though. We just did this last week, as a matter of fact. How do we put points in the calculator? That edit. Okay? So to put the points in the calculator, you followed a specific set of steps, which you went to the stat menu, and then you went to edit, and the X's went in L1 and the Y's went in L2. What was the one button you did not push in this menu? Delete. You did not push delete on the menu. Then after that, how did we calculate the equation? We went to find the equation, you went to stat, and went to stat, count this time, so we use our arrow and over to count. And now, we're going to have 3 different ones, because we're going to do the linear, we're going to do the quadratic, or we're going to do the exponential. We might have to do all 3. And it's really disappointing to watch some of you do nothing that you should be doing. So you're either going to hit 4, 5, or 0. Very disappointing, actually. 4, 5, or 0. So on your calculator, calculator, go ahead and do number 6. Put number on that table, put number 6 in your calculator while I'm waiting on mine to pull up. Number 6. Put those numbers in your calculator. You're going to put your X's in L1, your Y's in L2. Don't look at anything that's up there right now, because I don't know what this thing is doing. Don't look at what's up there. Everybody got those points in L1 and L2? Alright, go ahead and calculate a linear regression. So you're doing the stat calc 4. And then stop right there. Goodness. It's a refurbished one. The beggars can't be choosy. Call something. It's about to fix my fish here in a minute. So don't start doing something. What would y'all do if I smashed my fish through that screen?
I would offer you a paper. I would be
Yes, sir. your grades, you can redo any homework papers, things you have been able to do all year long. If you did it on Power School, you had to do it to register. Again, Skylar. Mind your own business and keep your hands to yourself. Kyle, you definitely be well served to mind your own business. Both go and you both have 90 seconds starting now. I told them they have 90 seconds to go and get back. Don't shut it because it'll work.
You have 4 seconds. You can't go to the bathroom. You put the bathroom on the floor. Yeah. Take a little bathroom. 30 minutes later, you come back from work. He takes up the time,
Okay, like I said, clear, I'll make sure your plot 1 is turned on, so go to second y equals. And when you do that, your plot 1 should be on. If it isn't, you need to make sure it's turned on, so you just hit number 1, and you make sure on is flashing. If off were on, if it were off, it would look like this. You want to make sure it's on, so make sure on is highlighted and hit enter for your stat plot, okay? This plot 1. Now I've got to go in and put in these numbers. Whoops, let me clear this. Okay, so I have them all in here. So y'all are already supposed to have these in here, and you are already supposed to do stat calc 4, right? Stat calc 4. Now, how many of you stored this equation? Because we need to graph it. How do you store the equation? You don't lay back in your chair. You go to alpha. You got to go down to store regression equation, and you do alpha trace. Alpha trace, and we're going to put it in Y1, so we hit number 1. So we're just telling the calculator we're putting this in Y1, so we don't have to type it in. And we're going to hit calculate. So you get an equation like this. Alright, did you get these numbers?
No, I don't know. I got A and B.
Okay, so now, you don't have these numbers right here possibly, do you? And these numbers are very, very important. Anybody remember what this is called? We've already gone over this. What is the big one? Well, unless you can get it coming out your mouth, it's useless in your head. So does anybody know what R stands for? We've talked about this over and over and over. It is called the correlation coefficient.
Man, I was about to say that.
Yeah, correlation coefficient. This is very important. I don't know if it's 2 R's or 1, may not be any. Why are we talking when we should be writing? Correlation coefficient. Should be writing correlation coefficient. You will have several questions on your ESC about this. And you have to know where it is, and you have to know how to turn it on. Because your calculator is going to be taken up before you take the test, and they're going to be reset. So you have to know how to go back and turn this on. So on your calculator, you're going to go to mode and stat diagnostics. If it says diagnostics, it must be on. So go to your calculator under mode, find diagnostics. Doesn't have to look exactly like mine, but find diagnostics. You may have to use your arrows and go down and turn your diagnostics on. Meaning you've got to go and highlight it and hit enter. So on is highlighted. And once you do that, then go back in and do stat calc 4. Put it in alpha, y1. You gotta use your down arrow. You gotta go to mode. You gotta use your down arrow to go to diagnostics. Make sure it's turned on. Once you do that, you've got to quit and then go back in and say stat calc 4. Make sure these are on L1 and L2, so that's where we put our numbers. Go to slow regression equation, get alpha space 1, and calculate, and you should now have the R2 and the R in there. You must know how to turn that on. So you're going to get a question on that on the test. It's going to say, what's the correlation coefficient? Well, if you can't turn it on, then you're never going to know what it is. So you got to know how to turn that on.
Is there a way to find it?
Yeah, but I'm not going to spend 30, 45 minutes showing you how to calculate one number. Yeah, there most definitely is a way, yes. Alright, so on the correlation coefficient, it can go from -1 all the way to +1. So if it's a perfect negative correlation, then it's a -1. If it's a perfect positive correlation, then it's a +1. Now 0 is right in the middle, and 0 means that there is no correlation whatsoever. No correlation whatsoever. So a negative correlation would be the more time you spend playing video games, the lower your grade will be. The more time you spend spending playing video games, the less your grade will be, the lower your grade. That would be a negative correlation. If one goes up, the other goes down. A positive correlation would be the more time you spend studying, the higher your grade goes. If one goes up, the other goes up. It's true, that is true. Alright, so you've got a perfect negative correlation and a perfect positive correlation, -1 to +1. The closer it becomes to 0, the worse it is. So a strong correlation is going to be, let me just get us a new page. Oh, Lord of mercy. Alright, so from -1 to +1, we're over here. And then at 0, there's none. So this is a perfect one. We'll talk about that. This is a perfect one. Now, anywhere from about 0.9, or from negative or well, that should be negative. I don't know how I did that. From -1 to maybe -0.9, It's called a very strong negative or a very strong positive, whichever the case may be. So you're going to get decimals. So a positive 0.9 or very strong. The closer it gets to 0, and you're going to see it down from 0.8 down, is called a weak correlation. So from here and on to here is a weak. Now, they're going to give you something on your EOC, and it's going to say the correlation coefficient of, I'll just use the same one I had, of the amount of time you spend playing video games versus your grade is negative 0.98. They're not going to say R equals. They're not going to give you that hint. Hey, we're doing this in the calculator. You're going to have to remember, correlation coefficient, that's that negative 1 to 1, meaning it's either a really strong positive or really strong negative. So just by telling you that, what would you say? It's not a perfect one, but it is a very strong one. Now, here's what your answers are going to look like. And I'm going to go quickly on this. They're going to say, let's see, what did I say? The number you play games versus what did I use? Grade versus your grade. And so we talked about the more you play games, the lower your grade. If one goes up, the other goes down. So an answer might be the more you play, the lower your grade. If we wrote all that out, right? The more you play, the lower your grade. I meant to write that above here. So A might say there's a very strong negative correlation. B might say a very strong positive correlation. Then it might say a weak negative or a weak positive. And the only thing you have to know is that the closer it is to negative 1 and 1, the better it is. So just by knowing that negative, we don't even care what we're even talking about, just by knowing that negative 0.98 is a really strong negative, you've got your answer. This is what I'm talking about. This will come up on the EOC on the non-calculator active. You didn't need your calculator to know this. They're just going to give you that, or they may even say R. They might say R equals. They may just give you a number, and you've got to be able to realize that. So questions on this one. We've talked about correlation coefficient before, but I've never given you these types of answers. So we're good there? Okay, so now, back to the calculator where we started. This is what we got. So what would you classify that correlation as? A very strong positive. You got to tell me positive or negative. So that'd be a very strong positive correlation. All right, now we're going to use those same numbers that we had in there, and let's this time, instead of doing a linear regression, let's do a quadratic regression. Number 5. So wait a minute, we said on this one R was, what was it, 0.95? So the linear R was 0.95. I'm going to do all 3 of them. Alright, so the quadratic, so stack count, this time we're using number 5, quadratic regression. We're going to store it, but we've already got our linear one stored in Y1. So we're going to put this one in Y2. So alpha trace, this time number 2, and then calculate. Let's just look at it. And so that one's got a 0.9. So quadratic of 0.9. And then we're going to do the exponential. So stat, calc, and remember exponential is that it's a 10, but they don't put 1 0, they just put a 0. So you can, it's easier just to go, you can go up or down, doesn't matter. Or you can just hit 0 actually. So exponential regression, now we've got linear Y1, quadratic in Y2, so we're going to store the exponential in Y3, and calculate that one. So we're telling the calculator, hey, put these all in our grapher. Oh, what did I do? I messed up. Did it give it to us? This value entered is not allowed in the function. Then it gives us radian and degrees. Oh. Well, one of two things has happened. Either we typed in numbers wrong, so at this point we say, uh-oh, let me hit quit. Let me go back to my numbers, make sure I typed them in there correctly. So I'm going to say, okay, I've got all my numbers in there correctly. What the calculator is telling you, you can't do an exponential. It's not an exponential, and the reason is 0, 0 is not an exponential. At that point, remember on that exponential, they always go through that point 1, 0 unless we shifted it some. So 0, 0, that point that we have on there, well, it's not going to work. But based on those two, which one's the better one? The linear one. Now, let's go back and try to graph it. Because everything's in there, it put all our equations. We may not be able to see them all. Remember I told you calculator sometimes is too smart for its own good. It's giving us every decimal that it can, when really we only need like 2 decimals. So I'm going to graph it and see what happens. Now I have no idea what my window's on, so what should I probably do? Zoom. What's the standard? Zoom 6. I always start at Zoom 6 and kind of work your way from there. So there's our point, our linear, and there's our quadratic. Remember, what's a quadratic? What is its general shape? It's a U, right? It's a U. Either it opens up or it opens down. So I have no idea what that quadratic looks like, do I? I'm going to do Zoom fit, which is Zoom 0, to see if it'll fit it better to it, just to see. Well, there's my line again. There's that quadratic again. It's not helping me too much, is it? At this point, what I would say is, you don't want to waste a whole lot of time on those questions. So you don't, I mean, you have 4 hours, but you don't want to waste a whole lot of time. I would, number one, make sure you look at the correlation coefficient. Which one was better? The linear one. I would go with that. What's the other thing we can do to these points? What did we just learn how to do? Use the table. Use the table. Which one did we have? We did, I forget which one I told you, number 6. Was that it? Hello, McFly. Is that it? Thank you. So you have these numbers. What do we do with the table? What did we just do? No, what did we do when we were given a table? We subtracted. We found the difference. So the first difference, so help me out. Use your calculator. Negative 18 minus negative 6. Negative 12. Negative 6 minus negative 2. Negative 4. Negative 2 minus 0. Negative 2. 0 minus 2. 2. 2 minus 6. Negative, I forgot to put the negative. 6 minus 18. Negative 12. Are all those constants? No, that's not linear, is it? What do we do on the second one? Negative 12 minus 4. Negative 12 minus negative 4. Negative 4 minus negative 2. Negative 2 minus negative 2. Yeah, negative 2 minus negative 4. And negative 4 minus negative 12. Is the second difference constant? No. So these numbers weren't the same. First difference is not the same, so it's not linear. These numbers were not the same. So the second difference wasn't constant, so it's not quadratic. We're doing something in group. So, cut the stuff out of here, so just
Okay.
come back.
Alright.
Where y'all going? Okay, alright, city girls. Alright, so let me go back. So the first difference is not constant, so it's not linear. Second difference is not constant, it's not quadratic. Is it exponential? Does it increase really quickly? Not really, does it? So what is this one? Neither. It's none of them. But you've got to be very careful though, because we had these, didn't we? So be very careful. But looking back at that graph, what would you have guessed? Linear. So you've got to be careful. Okay, now over on the top. I can't see what I'm doing here. It says training heart rate. So you've got A's of 20, 30, 40, 50, and your beats per minute of your heart rate. So let's put that table very quickly in this so we can get through this last one. Put that table in your calculator. So go to your calculator, stat edit. Remember, do not hit what? Delete. Do not hit delete. Hit clear. Put those numbers in there quickly. I won't. Didn't hit enter. There we go. 2034. Enter. Enter. There we go. Now let's just think about these common sense wise. We're talking about your training heart rate. Your age versus your training heart rate. Now let's think about this. You start out at age 20 and you go to age 50, right? You should, when you are younger, you should be able to be more active. Would you agree with that? Okay, you could do more. You could exert yourself more. So your heart rate, it's okay for it to be higher than versus whether you're 50. You don't want your heart rate to rate, okay? Now, think about this. Linear, exponential, and quadratic. So linear, quadratic, whether it goes that way or that way, is linear. And exponential can increase or it can decrease. All right, now let's logically think about this. Let's start down here. The older you get, does your heart rate climb exponential? Does it climb really, 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 really fast and never stop? No, well, it might if you did. Okay? Quadratic. Does your heart beat, because this is the y-axis, does your heart beat go all the way down to wherever and then spike back up? No. Okay? So would you agree, common sense, we're thinking probably linear right here? Okay, so all right, so we're back in here. We've got our numbers in here. Let's do an exponential, or not exponential, a linear regression. So stack calc 4 stored in y1 to alpha trace 1 and calculate. Sorry about it. Anybody else get that? Okay, so on that first blank it says, does this data represent a linear, quadratic, or exponential function? What would you put? Linear. So write linear on there. And it says, what is the equation of the function that represents the data? Well, what is our equation? Y equals negative 0.85x plus 187. So write that on the second column. Or you could go to your y equals and look at y1, right there it is. Y equals negative 0.85x plus 187. You could draw the graph, but we're not going to worry about the graph right now. Okay, turn over to that last page. You see 4 graphs right here? This is your homework. You have 4 graphs. You're going to type each one, L1, L2, L1, L2, and you're going to decide, is it linear, quadratic, or exponential? Now you've got a couple of ways you can do this. You've got to do the equations, and you might as well put it in the calculator anyway. You can also look at your table and do what we did before, the first differences, second differences, get you an idea. I'm not quite sure why everybody's packing up, because we still have a according to my calculations, 10 minutes left. So everybody get your calculators back out, because you're gonna at least put the first one in there. We're not packing up 10 minutes early, especially when we're failing. Excuse me? Remember, you always put 4 minutes of my time, so what happens? I'm not gonna hold you 4 minutes, but I'm definitely not gonna let you pack up early. No, because we're not done with this. So you get your calculator out, and we're gonna do this one. Well, that's your fault, because I gave you one. And there's 10 sitting right over there. So unless you're invalid, you can get up and get one. So, everybody put in the first one. Everybody put in the first one. Get at least one of them done. I see the first one, and you got the equation, and decide what it is, then I'll let you pack up. And nobody packs up until I see that first one. I want to see the equation for number one. Should be able to have some kind of guess about which one you think it should be based on the points.